Welcome to the trigonometry lecture. Some say that trigonometry is the most boring area of maths. Some even consider it horrible. But I think trigonometry is perfectly splendid because it offers so many opportunities for assessment. Anyway, trigonometry is so omnipresent in geometry that every game developer, just sooner or later, will encounter some kind of trigonometrical problem. The good news is that trigonometry is not based on overly extensive or complicated maths. The bad news is that practice can sometimes be quite tricky. This lecture concentrates on a theoretical basis for trigonometry, and it won't go much beyond what was taught in the basic GCSE course of mathematics. It's not also going to be very long, actually I have no idea how long it is going to be because I'm right now recording it, but you can check it somewhere here. So, moving on, the first topic must be Pythagoras Theorem. Pythagoras Theorem was taught so early in your education cycle that I'm not going to sacrifice more than 5 seconds for this topic. This theorem is about the relationship between the edges in a triangle. The edges in trigonometry are quite often marked with letters A, B, and C. But trigonometry, much more than being about edges, is first of all the science of angles. The angles are also quite often marked with the letters A, B, and C. But this time the letters are uppercase, so to make a difference. However, mathematicians even more often use a slightly different convention of using Greek letters alpha, beta, and gamma for the angles. This convention is very popular in scientific literature and in many web sources. You can actually freely choose whether you want to follow the Romans and use the Latin alphabet like ABC, or follow the Greeks and using alpha, beta, gamma. In our lectures, I will use the Greek letters, alpha, beta, gamma, but you are absolutely free to choose the system that you prefer. Now, this triangle has also one more very important aspect, and this is the right angle. The gamma angle here has the measurement of 90 degrees, and we call it the right angle. It's so important that in trigonometry we even have a special graphical symbol for the right angle. And why is the right angle so special? Because a big chunk of trigonometry will only work with right triangles, so triangles that have a right angle, like those two in the upper row, and this one here, which maybe doesn't look like a right triangle, but if I only rotate it properly, you can see it has the right angle, it's the right triangle. So in trigonometry, you have always double check if the triangle is right, or otherwise you may be very wrong. Be right, not wrong. Now, if we only concentrate on one angle, like this one, then we can adopt another way of naming the edges in a triangle as this one. A for the adjacent edge, the adjacent to the angle, of course. O for the opposite, and H for the hypotenuse. Moving on. Angles are measured in degrees, and the right angle is 90 degrees. It sounds quite obvious, but what is the mathematical meaning of 90 degrees? It's actually related to the fact that the full rotation, the full circle, is subdivided into 360 degrees. And the first to do it were, not surprisingly, in a trigonometry lecture, again, two ancient Greeks, the Aristarchus of Samos and Hipparchus. Most probably, the 360-degree subdivision was reflecting the annual rotation of the Earth around the Sun, so that 1 degree could roughly correspond to 1 day. Of course, this interpretation has no real mathematical meaning. For the angle measurement, which would be based on the solid mathematical foundations, we have to move to the 18th century Cambridge, where the British mathematician Roger Coates, a collaborator of Isaac Newton, introduced something that was called, not by him, the name came sometime in 19th century, but he proposed something that we now call radians. What is a radian? Why it has such a fundamental mathematical meaning? Radians is based on a rotation around a circle. So we start with this circle with radius r, and the diagram now shows the situation when our angle is 0 degrees, means 0 radians. Now, making this angle wider, we arrive to the situation in which the length of the arc at the edge of the circle is equal to the radius of the circle. And this is how we define 1 radian. 1 radian is slightly above 57 degrees, so it's not a very practical measurement for everyday use, but it has this deep mathematical meaning, which makes many mathematical formulas, and we will have examples of this in the future. Many mathematical formulas just simplify if you use the radian-based angle measurement rather than degrees. Okay, going further, we arrive to the right angle, 90 degrees, and in the radian measurement, it's exactly 1/2 of the number pi. So you now have to see that if something has pi in it, it must have a deep mathematical sense, and indeed it has. Going further, the half of the full circle on 180 degrees, it's exactly pi radian, and the full circle, 360 degrees, is 2 pi radian. Moving on, the next diagram shows, first of all, very useful formulas to calculate radians into degrees and degrees into radians. Most software libraries will have a function like this, but in case they don't, you can always use this slide that quickly summarizes everything that you should know about conversion between radians and degrees. Down here you also have the value of the number pi at 2 different levels of accuracy. Moving on to trigonometric functions, but first of all, what is a function? A function is a relation between two sets that associates every element of the first set to exactly one element of the second set. So, for example, every value of alpha from the left column of this table gets exactly one value of sine alpha shown in the right column in this table. In programming, function has a very similar meaning. So again, a function takes one or perhaps more parameters, does some calculation and returns exactly one value, one result of a well-specified data type. By the way, this function is a C++ numeric calculation of the value of the sine trigonometric function, but you don't have to use a function like this because C++ provides us with a mathematic library called math.h, which provides sine, cosine, easy to use, ready to use, first of all, functions. Back to the mathematical functions, the values of function can be shown on a diagram, on a system of coordinates. So the x, the horizontal axis, shows various values of alpha from 0 to 2 pi, and in the vertical direction we can see the values of the sine function. Now we can add more data points, or even more data points, creating eventually a diagram of a function. And now we can move on to
Soh-Cah-Toa, 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 Soh-Cah-Toa.
Yes, definitely secondary school maths. So, to find the values of trigonometric functions of this angle alpha in a right triangle, first of all you have to find the adjacent edge, the opposite edge, and the hypotenuse. A very important point here is to ensure that between the adjacent and opposite edge there is a right angle. If this angle is not right, your trigonometry will be wrong. So it's really, really important. But if it is right, then feel free to use these splendid Soh-Cah-Toa formulas. In real life, however, you won't probably work with the edges called or named opposite, hypotenuse, adjacent. And if you are lucky, they will be named like this, just A, B, C. The corresponding formulas are here. For example, for sine alpha, it's the opposite edge, which is A, divided by hypotenuse, which is C, A over C. But in real cases of trigonometric problems, it is usually not about finding the value of sine alpha, but rather finding the length of one of the edges of the triangle. So, for example, you can know the value of the C, the hypotenuse, and the value of sine alpha, and this will allow you to find the value of the opposite edge A. Or you know the A, the opposite edge, you know the sine alpha, and you need to find the hypotenuse. So this is a kind of quite essential transformations of the basic formula. And to get these transformations right, it may be very useful to use this informal structure, triangular structure, in which this line symbolizes the fractional line, this one, and this line symbolizes multiplication. How to read this structure? So, first of all, sine alpha is A over C, so that's this formula here. Then A equals C times sine alpha, okay, that's this formula. And finally, C equals A over sine alpha, and this is this formula. Here are the formulas, corresponding formulas for cosine and tangent. typical problems solved with Soh-Cah-Toa. We have this triangular structure that represents a hill. The slope of this hill is 20 degrees. The length of the baseline, so the edge L of the hill, is 100 meters. So what is the height? Okay, so once again, the question is, we know the angle, we know this edge, that's the adjacent edge, and the question is about h, which is the opposite edge. The question is, which of the three trigonometric functions, sine, cosine, or tangent, should we use? It's a pre-recorded lecture, so I can't hear any answers, but I hope that you answered tangent alpha, which is opposite over adjacent, so h over L. From this formula, we can find that h is L multiplied by tangent alpha. L is 100, tangent alpha is 0.36 something. The result is slightly more than 36 meters. Another example. The slope gains 5 centimeters per each meter of length. What is the slope? What is the angle? Again, the question is it sine, is it cosine, is it tangent? And of course, it is again tangent, because we get 5 centimeters gain in the height per each running meter of the length. So tangent alpha is again h over L, and we need to find, and typically, in most cases, the trigonometrical questions will be about the length of the edges of a triangle. Here, the question is about the angle. So we can easily find h over L. It's 5 centimeters over a meter, so 5 over 100 is 0.05. And we have to find the angle that corresponds to this value of tangent. To find it, we can use the function that is the opposite to tangent, so a function that takes the value of the tangent and returns the angle. And the answer is 2.86 degrees. The final example here, the length of the baseline of the hill is 100 meters. The height is 10 meters. The length of the slope is, and if you think whether it is sine, cosine, or tangent, first of all, look, in this question, there are no angles. Yes, this is Pythagoras. Okay, we'll find it from Pythagoras Theorem, and the necessary calculations are displayed on screen. Moving on to trigonometric identities. This is a set of very useful formulas, which you should, if not memorize, keep in a visible place within your notes. The right-hand side formula allows you to find the value of tangent if you only know sine and cosine. But the left-hand side formula is even more important and useful, because it allows you to jump from sine to cosine. If you know the value of sine, you can find the value of cosine. If you know the value of cosine, you can go back to the value of sine. One thing, this notation sine squared alpha may be a bit confusing, but this is how mathematicians made this notation. Sine squared alpha means the same thing as sine alpha squared. So this is a squared of the value of the sine, not some kind of a strange squared function. So if you know what's behind this notation, it's quite easy. An example of a problem which can typically appear in in-class tests: if sine of 30 degrees is half, so what is the cosine of the same angle? And the solution is as follows. Cosine squared of 30 degrees from the trigonometrical identity must be 1 minus sine squared alpha. We know the value of sine alpha is, of course, in this case 30 degrees. We know the value of sine 30 degrees. It's half 1 over 2. So we can substitute this with 1 minus 1 over 2 squared. 1 over 2 squared will be 1 squared over 2 squared, so 1/4. 1 minus 1/4 is 3/4. That's the value of cosine squared 30 degrees. Cosine of 30 degrees will be the same value under the square root. So it's the square root of 3 over square root of 4. But square root of 4 is 2. Therefore, the result is square root of 3 over 2. With this, we can move on even further to this little table, which students sometimes try to memorize, but there's really no reason to memorize it. This table shows typical values of 3 trigonometrical functions for a range of values between 0 and the right angle. The only two things that you need to remember in order to fill in all the pieces, all the cells in this table, is that sine of 0 is 0, and this is something that is really, really useful to remember. Sine 0 is 0. And the second thing is sine 30 degrees is half. It's also reasonably easy to remember. So we will directly put these two values to the table, 0 and 1 over 2. Now we can do an educated guess. If sine of 0 was 0, then sine of the right angle, 90 degrees or half of pi radian, will be 1. And if you remember the shape of the sinusoid of the graph of the sine function, you should guess this reasonably easily. Now, another educated guess, if sine at 0 was 0, then cosine at 0 will probably be 1, and cosine in 90 degrees at the right angle will be 0. In fact, sine and cosine are like mirror reflections. So we can at once put here that the value of sine 30 degrees will also be the value of cosine 60 degrees, the other side. All right, next thing, cosine of 30 degrees. For this, we will use the calculation we've just done in the previous slide, and this was square root of 3 over 2 goes here, and mirror-like also here. The final calculation for sine is the sine of 45 degrees, or a quarter of pi. But 45 degrees is a very specific angle because it's exactly half of the right angle. So if you imagine a triangle which has two edges, both adjacent and opposite equal to 1, and actually it doesn't matter which is adjacent and which is opposite, because if this angle has 45 degrees here, it also will have 45 degrees here. So we can quickly find the hypotenuse using Pythagoras. So c squared is 1 squared plus 1 squared, it's 2. So c is square root of 2. And now the value of sine of 45 degrees will be 1 over square root of 2. So it's square root of 2 over 2. And the cosine of 45 degrees, because this triangle is exactly symmetrical, will be the same number, square root of 2 over 2. And in this way, we've done all the values for sine and cosine. Now the time came for tangent. Tangent, as you may remember from the previous slide, the trigonometrical unity for tangent says tangent is equal sine over cosine. So sine over cosine, 0 over 1, it's 0. 1 over 0, it's infinity, and that's true. Tangent and at the right angle is the infinity. Then we have an easy case here for 45 degrees. This is square root of 2 over 2 divided by square root of 2 over 2. Same number divided by same number is always 1, so tangent of 45 degrees is also 1. Here there is a little bit more complex calculations. You can do this calculation in your spare time. I will just show the result. It's square root of 3 over 3, and for this case, by dividing this number over this number, we get square root of 3. And in this way, our table is complete. With this, we can move on to the diagrams of trigonometrical functions. Here you can see combined diagram of sine and cosine function. Sine is red, cosine is green. Very important thing to remember, sine of 0 is 0. And you don't need to remember anything else than that, because if you only remember that sine and cosine start at two different levels, so sine at 0, cosine must start at 1, so cosine at 0 will be 1. Then sine at the right angle from 0 will go up to 1, cosine at the same time will go down to 0. If you look into this diagrams, you can also discover the values for negative alpha, sine and cosine of negative alpha. So this is sine and cosine. This is the diagram for tangent. Tangent again starts from 0, just like sine, but by the time it arrives to the right angle, the value of tangent approaches infinity. Moving on, and on to the final topic today, trigonometry of any triangle. Earlier on, I stressed very much that the Soh-Cah-Toa formulas must not be used unless the triangle is right. And this remains perfectly true, but what to do if the need is to solve a triangle that has no right angles? And this solution is reasonably simple. We need to make right triangles out of this one, and we can do it by dividing the triangle into two smaller ones. As you can see, each of them now has a right triangle, so Soh-Cah-Toa is applicable. For example, for one triangle we get sine beta equals h, that's the opposite, over a, that's the hypotenuse, and for the other one it is sine alpha equals h over b. We use here the observation that the edges a and b, so this and this, of our big triangle are now hypotenuses of the smaller ones, and they both share the same opposite edge to the angles alpha and beta, which we called h. Therefore, for each triangle, we can find the h as follows. It's for one triangle it's a sine beta, and for the other b sine alpha. As the left sides of these two equations are equal, so must be the right sides. So we can rewrite this equation as follows, and one more transformation, and we get something that is known in mathematics as the sine rule. It can be further extended to a part representing the C edge and the gamma angle. This formula helps to solve any triangle, even a triangle that has no right angle in it. Apart from the sine rule, we also have the cosine rule, which allows for finding any edge, for example C, if we know the two other edges, like A and B, and the angle between them. And this is in fact a generalization of the Pythagoras theorem. So, there are all the key facts about trigonometry that I prepared for you today. But to succeed in this fascinating but challenging area of maths, it is essential to get some practice. All formulas are useless unless you have not only the knowledge but also experience in using them to the real-world problems. So I invite you to study all additional material published in Canvas, as well as a collection of practice video recordings. And before this presentation is over, I will present one more final slide, the take-home message, or everything you really need to know about trigonometry. But I am saying goodbye to you right now, and thank you for watching.